In this lecture, we will discuss about airfoil characteristics, aerodynamic center, and we will revisit elementary flows. We will discuss about CL, CD, CM variations with angle of attack, that is alpha. There is a book authored by Abbott and von Doyenhoff, which has a very rich collection of experimental data regarding airfoil characteristics. So, the book is named Theory of Wing Sections. If you manage some extra time, you can go through this book. Let us try to visualize the test section of a low speed wind tunnel. So, it is drawn in a cross sectional sense. Let us imagine that the flow velocity is moving into the inlet part of the test section. We are trying to sketch the test section in more like an isometric sense, and then considering the features to be transparent, as if we can see through the different objects placed in the wind tunnel, we can imagine that an airfoil model is mounted in the test section in such a way that it is spanning end to end of the test section. That means, it is reaching out to the two side walls. In such a situation, we consider this to be a case of an infinite wing. That means, a wing without any ends, while if it was not spanning up to the two side walls, if there was a gap between the side wall and the edge of the wing, then that would be called as a finite wing. Though strictly speaking, for an infinite section, the span should have also been infinite. That means, if this is say negative infinity, that is positive infinity, then typically this section should have spanned to plus minus infinity, but that is not possible to do in a physical situation, and therefore, it is spanning up to the ends of the test section. Now, if you try to make measurements of the forces directly using load cells, which are used in so called wind tunnel balance, then you can make direct measurement of forces, like you can get the normal force coefficient out of it or axial force coefficient out of it once you have made the measurements. So, this is how you would like to do it experimentally. In the earlier times, this was possible only by experimental means. Today, we also have computational fluid dynamics to simulate the flow using computations. Now, we discussed about symmetric and cambered airfoils last time. Let us imagine that we have tested a symmetric wing and a cambered wing, or rather infinite wing, which means an airfoil in the test section of a wind tunnel, and we are plotting the data. Then how would the plot look like? For a symmetric wing, the plot would look more like this. For a cambered wing, it would look more like this. There is something called as a zero lift angle of attack. That means, the angle of attack at which the airfoil generates 0 CL. So, what we find is that for a symmetric wing, it is 0 degree, while for a cambered one, it is generally a negative angle, typically in the range of about say -2 or 3 degrees. You can find that at the lower angles of attack or low to moderate angles of attack, the CL variation is linear. It becomes non-linear as it approaches the stall angle. The maximum CL that it generates is called as CL max. When we try to look at the linear portion of the lift curve, inviscid theory or potential flow theory can predict it. When it comes to CL max, then you need viscous theory, because it is a viscous flow phenomena associated with flow separation, which has to be accounted, and therefore, inviscid theory would not be able to predict CL max. Also, this linear portion, the slope of the linear portion, if you say d CL d alpha, let us name it as say alpha naught, then this alpha naught, it is not a very strong function of Reynolds number, but CL max is. So, this is strongly dependent on Reynolds number, which is obvious because the viscous effects vary depending on the Reynolds number. Next, let us look at drag coefficient, how CD versus alpha would look like. So, now let us plot CD on the y axis and alpha. Of course, we are plotting it in degrees. These are typical angles which are taken from some standard airfoil data. We are referring to the NACA 2412 data. You are already aware of the airfoil nomenclature. So, you would be able to identify what the numbers 2412 mean. Let us mark the numbers and then we will try to recall the values that we saw for the CL alpha curves, though we did not mark specific values, but if we were to mark those values, what order would they be? For example, for the same airfoil NACA 2412, the CL max is of the order of 1.6, while you can find that the CD is much smaller, it is almost 2 orders smaller. And that is not a surprising thing, because remember that the aerodynamic efficiency depends on the ratio, lift to drag ratio, and until unless that is significantly high, it is aerodynamically not efficient, not an efficient lifting surface. Now, let us plot the drag versus alpha curve approximately. So, it looks more like this. So, this is at around Reynolds number of 3 into 10 to the power of 6, that means 3 million based on the chord length. If you vary the Reynolds number, then you see some variation in the CD versus alpha plot. So, this is say approximately at 9 million. That means, as Reynolds number varies, you see distinctly the drag coefficient is changing, which is because it is dependent on viscous effects, and therefore, once the Reynolds number alters, the effect of the viscous forces vary with respect to the inertial forces. Let us try to use the same plot for indicating the moment coefficient. So, we will use a different color to show how moment changes as a function of angle of attack, and this value is about minus 0.05. So, this is the CM AC, which means aerodynamic center. We will soon see what that means. The important thing that we notice over here is that CM does not change with alpha, which is quite surprising, because CL, CD, they do change significantly with alpha, but CM does not. But that is as long as you take it about a special point, which is called as an aerodynamic center. In general, if you move to other points on the airfoil and you take moments, then the moment would be a function of alpha in general, but it would be constant if it is taken about the aerodynamic center. That means, there is this special point somewhere on the airfoil about which if you take the moments of the forces, then the d CM AC d alpha will be 0. Now, how do we try to identify where this point is? So, let us say this point is located at a distance of x AC from the leading edge, and you are locating your forces there, and you are defining your moment about that point as m AC. So, earlier you recall that we had located the forces at different other points like leading edge, quarter chord, center of pressure, etc., and we tried to find the connection between the moments. So, we ended up doing that, and we found that leading edge, quarter chord, those positions have separate moments associated with them, which we indicate as m LE, m c by 4, etc., while the moment about the center of pressure incidentally is 0. Now, about the aerodynamic center, the moment remains constant, it does not vary with alpha, that is the point. So, we can find this x a c provided we have a few details. We need to have the slope of the C L alpha curve, we need the slope of the C M alpha curve, and we need the lift, drag and the pitching moment about an arbitrary point. For convenience, let us set that to be m c by 4. Of course, L by d is irrespective of the point, it is the moment which would matter. So, if that is done, let us indicate this dimension in non-dimensional form as x a c by c. So, let us call it as x bar a c. In that case, if you were to go back to the quarter chord position and locate your forces there. So, in that case what would you have? You have m c by 4 and you have, let us say, this point aerodynamic center here, which is indicated by C x a c bar. So, then you can write the moment about the aerodynamic center would be m c by 4 plus the moment due to the lift being offset from that point by this distance. Now, you non-dimensionalize by dividing with q infinity S c. So, what is S? S is the planform area of the airfoil. So, it is basically the chord length into unit depth, and this is the chord itself. Q infinity is the free stream dynamic pressure. So, if you divide all the terms, then what do you get? So, m a c by q infinity S c, similarly m c by 4 by the same term, so one c will cancel over here, etc. So, you have C m a c is C m c by 4 plus C L into x bar a c minus 0.25, that is what you have. Now, we will take a derivative of this expression, because you remember that the condition is that d C m a c d alpha is equal to 0, that is the condition. So, if you take a derivative, what happens? So, this is what you have. By definition, this is equal to 0, because it does not change with alpha. So, finally, what do you have? You have d C m c by 4 d alpha plus d C L d alpha x bar a c minus 0.25 equals 0, that is the condition. And let us call this as alpha naught, and let us call this as m naught. So, what do you get? You get x bar a c is 0.25 minus m naught by alpha naught. Now, incidentally, if the aerodynamic center is precisely at the quarter chord, then obviously m naught has to be 0. Okay. So, it has to be basically parallel to the x axis. Now, what is found is that if the airfoil thickness changes, So, you have a basic camber line, but on that you are imposing different thicknesses, then the x bar AC will start deviating from this 0.25 gradually. Additionally, there is a special significance of this aerodynamic center for flight mechanics calculations, where you look at stability and control, and there it is particularly convenient to have a point about which the aerodynamic moment remains invariant with alpha. So, we discussed about the significance of aerodynamic center. Now, we will try to develop a theory of potential flow past a thin airfoil. That means, an airfoil whose thickness is not a very large value with respect to the chord length. And in order to look at this theory, we need to revisit our elementary flows. So, for that you recall that we had learned about Laplace equation. So, that was the equation governing incompressible irrotational flow, and you recall that because of the irrotationality there was a presence of a velocity potential, and we had discussed about developing a velocity potential for one elementary flow, that was uniform flow. Now, we are going to develop on the concept of elementary flows by looking at a few others. So, what are they? We are going to look at source or sink as the next elementary flow, followed by a doublet and then a point vortex flow. So, we have to look at these few more elementary flows. So, let us go ahead with that. Before we go into source and sink, we relook at our uniform flow. Remember that we had developed the expression for velocity potential as u infinity x. So, the velocity potential was proportional to x, and therefore, at different x locations starting from the origin, you would have different values of phi, say phi 1, phi 2, etc. If you look at the streamlines on the other hand, you would have different values of psi, the so called stream function. So, I will put it as psi bar and then indicate it. We will look at the significance of the stream function. So, along a streamline, the stream function, which is basically a function of x and y, remains constant. As long as we are following a particular streamline, the stream function will remain constant. And if you take the difference of the stream function between the two streamlines, let us say here, then the difference turns out to be C 2 minus C 1. And what is the physical significance of that? It is the mass flow between the two streamlines per unit depth perpendicular to the page. That is the significance of it. So, it has the concept of mass flow being accommodated between these two streamlines. So, where the local velocity is large, then the streamlines will get closer to each other, there will be rapid variation of stream function. When the flow velocity is slower, smaller, then the stream functions, the streamlines will be further apart and the stream function variations will be more moderate. Now, if it is a compressible flow, we can take the spatial derivatives of the stream function to obtain the mass fluxes. But if you take a derivative along y, you get a mass flux along u, negative derivative along x, the mass flux along v. It is different from what you saw for velocity potential, where the del phi del x was linked with u, the del phi del y was linked with v. For incompressible flows, we define the stream function slightly differently. We call it psi, and for doing that we divide psi bar, which is the compressible stream function, by the density, which is essentially taken to be constant. So, the delta psi then would represent the volume flow between the two streamlines per unit depth perpendicular to the page. So, that is how we need to interpret stream function. So, with that understanding, we go to the new elementary flow, which we call as source flow and sink flow. So, I will name it or number it as 2, because this is the second elementary flow. How does it look like? Let us draw some streamlines to understand the nature of the flow. Let us consider them to be incompressible. So, we have drawn some streamlines, we have drawn some iso velocity potential lines and indicated them here. In one case, you see that flow is moving out radially from a point source. Where is the source located? At this point O. Similarly, here it is moving in radially into a point sink. Since the movement is radial, therefore, it will be more convenient to make use of cylindrical polar system to indicate the velocities. So, the radial velocity in this case, is non-zero, while the tangential velocity is equal to 0. And in a cylindrical polar system, let us suppose you are indicating a point P, then its coordinates will be r theta, where this is the distance r from the origin and this is your theta from the reference direction. So, if I were to consider this as the x axis in Cartesian coordinates, then theta is measured counterclockwise from that x axis to reach the angular orientation of the point. Okay. Now, V r in this case, if you were to represent it simultaneously for a source and a sink, will be plus minus capital lambda by 2 pi r, r being the radial distance of a point. So, if the point is here, then this is the radial distance r. So, for source it is a plus, for a sink it is a minus, because in one case it is radially outwards, in another it is radially inwards. What is the significance of the capital lambda? It is the volume flow rate per unit depth perpendicular to the page. That is the significance of capital lambda. In terms of the velocity potential, we would find that del phi del r is equal to V r. We are working with cylindrical polar coordinates. Please take care of that. And if we integrate this, we will get the velocity potential, which will come out to be capital lambda by 2 pi natural log r. So, this is the description of velocity potential for a source. Similarly, for a sink it will be minus. We can show, if we were to do a calculation for circulation, we could have shown that both for uniform flow as well as a source or sink, circulation would turn out to be 0, which you can try doing as a homework problem. Now, as far as r tending to 0 condition is concerned, we see that V r would tend to infinity as we approach that. That means, V r becomes extremely large and therefore, you have a singularity at the point O. So, in this lecture we discussed about airfoil characteristics, which comprised of lift coefficient, drag coefficient and moment coefficient variation with angle of attack. The concept of aerodynamic center was introduced, and then we initiated some more discussion on elementary flows, where we looked at uniform flows once again, where we discussed about the stream function concept, and we then developed the concept of source and sink flow. Thank you.